This is a demonstration video for MAS applied to the mathematical library case study. MAS is a mutation analysis tool specifically designed for cyber-physical systems. MAS implements a set of optimization techniques that enables the applicability of mutation analysis and addresses scalability and accuracy in the CPS context.
To use the tool, we first need to configure it, and to do so, we are going to edit masconf.sh to define the installation path, the directory of the workspace, the type of build system, the compilation commands, the command for executing the test suite, the sampling technique to be used, among other optimizations. Please note that we provide a template that is already filled with most of the commands that you see. The editing is reduced to a few lines of script. The second step consists of editing the mutation script. For this, we are going to provide a function that executes a single test case of the test suite and then will return a success or a failure code. The third step consists of editing the prepared suite script. This script compiles the software, collects the compilation database, and executes the test suite. For each test case executed, we're going to need to invoke FACA's collect code coverage script and to measure the test case execution time. The first step of the methodology consists of executing the prepared suite script, where in addition to collect code coverage, we will also collect the list of tests to be executed. We can see the list of tests plus its timeouts on the following file. The next step consists of generating the mutants. For this, we are going to simply invoke the corresponding MAS launcher. All the mutants will be stored in the source mutants folder.
The next step of the pipeline consists of disregarding equivalent and redundant mutants with trivial compiler optimizations. To this end, we store the hashes of the compiled mutants for all the optimization levels. After compiling the mutants, we process the hashes to identify equivalent, redundant, and also non-compilable mutants. As you can see, we have identified 150 equivalent and 3000 redundant mutants. The next step of the pipeline consists of generating a prioritized and reduced test suite. This step will generate a file containing for each mutant a specific set of tests to be executed in a specific order. Then, we will execute a subset of the mutants. In this case, we have decided to use the FSCI sampling approach, which means that the technique determines the sample size dynamically while exercising the mutants, based on a fixed width sequential confidence interval approach. During this step, we will collect, in addition to code coverage, the mutation traces that include the mutant statuses, the tests executed, and the execution times. There will be one line per test executed. We also report a list of kill mutants and a list of live mutants. In the next step, we will identify equivalent mutants based on code coverage. In particular, we compare the code coverage of the original program against the coverage of the live mutant. Mutants that do not show a change in the code coverage will be considered likely equivalents. The mutation results will be updated accordingly, removing the equivalent mutants. In this case, we report the list of equivalent mutants as well.
In the last step, we generate a mutation report, which shows the mutation score, the number of mutants sampled, the code coverage, and shows a pointer to a list of live mutants to be analyzed by the engineer.